Let's start with question 6. It says, which are correct for reaction shown? If you look at this reaction, it's obvious that it's between a strong base and weak acid. So any acid-base reaction is called a neutralization. So we can exclude the formation reactions in here, and we could either have B or D. Based on the value of delta H, which is obviously negative, then it tells us that this reaction is exothermic. So definitely the answer is D. Let's just jump to question 7. It says 5.20 grams of sodium hydrogen carbonate is added to excess acid. Okay, the temperature increases and the energy change is calculated. So this is an exothermic reaction, and this is the Q value. What is the enthalpy change per mole of sodium hydrogen carbonate? If you look at the value that was given to you, it's in joules, and the answers are in kilojoule per mole, which means that we have to change the joule into kilojoule by dividing over 1000. So we can say 1030 divided by 1000, and then it's equal to 103. Okay, this is a kilojoule, but since it has to be per mole, we need to calculate the moles of sodium hydrogen carbonate, and the moles are equal to 5.20 over 84. So the answer is equal to 0.0619. So we divide this here, 0.0619. So the answer is equal to 16.63. And since it's an exothermic, it has to be negative. The answer is B. Now, question 8. 25 cubic centimeter of sodium hydroxide of a concentration of 2 molar was added to 30 cubic centimeter of ethanoic acid solution of a concentration of 1 in a polishing cup. The mixture was stirred, causing the temperature to increase by 6.5. What is the expressions for the enthalpy change of neutralization of sodium hydroxide in ethanoic acid? Assume that the specific heat capacity is 418, and this is the density of mixture. Okay, so first of all, we have to think about once we have a neutralization process, we are mixing the acid with base. So we have to think about the value of a Q that equals to MC delta T. The mass has to be the mass of aqueous solution. So the aqueous solution is composed of sodium hydroxide and ethanoic acid. So the total number of a cubic centimeter, 25 plus 30, it's equal to 55 cubic centimeter. But we are looking for mass in here. We need a mass. So there's a piece of information that was given to us, tells us that the volume is the same as the mass in here, which is the density. You know that the density is equal to the mass over volume. And since we have 55 cubic centimeter, then we have 55 grams. So we have to say it's 55. And we multiply by specific heat capacity, which equals to 4.18, and the increase in temperature is represented by 6.5 degrees Celsius. Now this is a Q. If we want to calculate the delta H, you have to divide over moles of water. But how many moles of water we have to do? Just keep in mind sodium hydroxide reacts with ethanoic acid CH3COOH, and since this is a typical acid-base reaction, we should have water plus a salt, which is CH3COONA. And we just noticed that the ratio is 1:1 in all. So which of these moles should I take? The moles of sodium hydroxide or the moles of ethanoic acid? It's based on the limiting reactant. If we calculate the moles of sodium hydroxide, it's 25. It's 25 over 1000 times 2, so it's equal to 0.05. And if we calculate it for ethanoic acid, it's 30 over 1000 times 1, so it's equal to 0.03 moles. Based on that, since the ratio is 1:1, the ethanoic acid is the limiting reactant. And that's why the moles of water will be the same as this ethanoic acid. So we have to divide this number here to be 0.3. And based on the answers, if you look, we exclude A and B because the volumes are incorrect. We have we could have either C or D since they have the same thing in here, but the only difference is in the number of moles. So we can choose D because it represents the limiting reactant. Let's just go again to another type of equations that was repeated and the first or the second. The measurement uncertainty and thermometer used in experiment is plus minus 0.5 for each value. What is the percentage uncertainty? So we have a rule for that. If you remember, it is the uncertainty over the reading of delta t times 100. And since we remember that delta t is two values, delta t is t final minus t initial, we have 0.5 in here and another 0.5 in here. So we multiply them by 2, we got 1. So the answer is 1 over delta t. It's 6.5 times 100. And the answer is 15.4%. So the answer is C. Just keep in mind, just for having a common sense, in any experiment that improve delta t to be high, it will lead to decrease the uncertainty a percentage, which is good. So the lower temperature will have a lot of uncertainty percentages. Question 9, and it says, when 50 cubic centimeter of hydrochloric acid of a concentration of 2 is added to 50 cubic centimeter of sodium hydroxide of a concentration 2. So you can notice that we have equal amounts of both, same moles. The temperature increase, I mean delta T, is equal to 13 degrees Celsius. And the experiment is repeated using 25 cubic centimeter of same hydrochloric acid and 50 cubic centimeter of sodium hydroxide. What is the temperature increase? All right, just recall again. Delta T increases with decreasing the water or the aqueous solution. It increases with increasing the moles of the acids or the base. Now, if you look at the question in here, the volume that we started with was in total, like we have 100 at first, 50 plus 50 is equal to 100 cubic centimeter. And now it turns to be less than, it turns to be 75 cubic centimeter. So this is a credit for us. We can say like delta T will increase for sure in this case. But the only thing that decreased in this case is the number of moles of hydrochloric acid. So at this point, the hydrochloric acid is the limiting reactant. If we calculate the moles before and after for hydrochloric acid, HCl, before and after. So let's start with the before one. It's 2 times 50 over 1,000. So it's equal to 0.1. But after it becomes 2 times 25 over 1,000, and now it's 0.05 mole. So what happened to the moles? It's decreased. Decreasing the moles will decrease delta T. Okay, so we have decreasing the moles. Now, how can we write the ratio? First of all, delta T will increase if we decrease the volume. So we divide 100 over 75. And we said that because decreasing the volume of water leads to increase the delta T, and that's why we take the big number to be divided over the small number. And then we say multiply. We have two moles, 0.1 and 0.5. It was 0.1 and now it's 0.05. So the delta T will decrease. So we take the smaller value over the higher value. So it's 0.05 over 0.1. And then we multiply by 13 degrees Celsius. Now, if you apply that in your calculator, you will end up with 8.67. So this is the change in temperature, C. Question 10 says, in an experiment, 50 cubic centimeter of 1 molar of hydrochloric acid reacts with 50 cubic centimeter of sodium hydroxide. This is a neutralization reaction. The specific heat capacity of the mixture is 4.18. What temperature change occurs in this reaction? So we need delta T, but we have joules, which is the Q value. So Q is equal to mc delta T. The Q is equal to 2,500 joules, and the mass is equal to the mass of solution. We have 50 cubic centimeter, and we have another 50 cubic centimeter. The total is 100 cubic centimeter. And since the density of the aqueous solution is equal to 1 by default, then So the volume is the same as the mass. So we have 100 grams of aqueous solution. So it's 100. And the value of C is equal to 4.18. And then T is the unknown. If we divide that on like 100 times 4.118, same thing here, delta T is equal to 5.98 degrees Celsius, which means it's 6.0. The answer is could be A or D. And since this reaction is a neutralization, it's an exothermic, and it has to be delta H with negative sign. So the answer is A. It's an increase of 6 degrees Celsius. The question says excess zinc powder is added to 50 grams of 0.5 moles of copper sulfate solution. In a polishing cup, the mixture is stirred and the maximum temperature change determined. The enthalpy change for the reaction is calculated to be negative 185 kilojoule per mole, and the data booklet value for this reaction is negative 217 kilojoule per mole. What is the percentage error in this experiment? You have to keep in mind the percentage error is not the same as the percentage uncertainty. It has a law, and this law indicates that you have to take the absolute value of the difference of the two values over the true value times 100. So the difference, as we can notice, we can say negative 100 of 5 minus 217, and then you divide it over 217. And for sure, we take the absolute value, we don't care about the sign in this case, and we multiply by 100. And if you apply that in your calculator, you will end up with 14.7%. So the answer is C. B says in the calculation, the specific heat capacity of liquid is taken to be 4.18 rather than the true value of 385. The use of 4.18 in the calculation. Just keep in mind the delta H is equal to MC delta T over M. The value we got is negative 185 kilojoule per mole. The value FC used was 3.85. What happened if we use the value of 4.18 instead? For sure, as we increase the value of C, the delta H will increase. I mean, it becomes closer to the value of negative 217. And since it gets closer to the 2.217 kilojoule per mole, we are lowering the error percent in this case. If you just mention this in here, we go back again to this question. If this value gets closer, let's say it becomes, let's say 200, negative 200. If it gets 200, then this difference or this error percentage will be lower. So technically, we can check the answers and see what happened. It's partly responsible for the error and the final value obtained. No, it's not responsible. It's the opposite. It improves the result. It lowers the error in the final value. Yes, this is definitely the answer. We are using higher value of specific heat capacity, and that's why the delta H will be more exothermic. It will be closer to this value, and that's why the error percent will decrease. So the answer is B. All right. We're going to talk about how to write or how to represent the enthalpy change of formation equation. Just keep in mind we should have three conditions. The first condition, you should have 1 mole of a product. And the second thing, you should have reactants to be elements. And the third condition, all products and reactants have to be in their standard state. So if you want to define the enthalpy change of formation, it is the enthalpy change when 1 mole of the product is produced from elements under standard conditions. Now let's start with these equations. Which of these represent the standard enthalpy change of formation? At the beginning, we can directly exclude C and D because both have 2 moles in their product, so they are incorrect. We could either have A or B. So let's start with A. We have 1 mole, that is correct. It comes from element. Yes, it's in O2. This is aluminum. Good. The third conditions are in their standard state. This is solid. Yeah. This is gas. Yeah. This is solid. That's so good. But why B is wrong? Yes, B is wrong because the oxygen is not in a standard state. It's 3O and it's not a standard state. So the answer definitely it's A. Let's take another question. Question 14 says we have this beautiful equation, which is correct, simple for the enthalpy change for this reaction. First of all, it is atomization. No, it's not. The atomization indicates to break the bonds between the atoms, and this is definitely, it's not an atomization. It's not a combustion product because we have, you can see 2 moles of carbon. And just one more thing, the product is carbon monoxide. In combustion, the product has to be carbon dioxide. So this is not. And for C, it's, you notice that we have 2 moles of carbon monoxide. It's not acceptable for formation. It has to be 1 mole of a product. Definitely the answer is D. Now let's jump to question 15. Question 15 indicates to the Hess's law, like Hess's law principle. It could be solved by equations and it could be solved by cycles. Now we're going to apply the equation first. How can we solve this question? Now let's read this question carefully and see. The enthalpy change for the two reactions are shown. We have these these two beautiful reactions with their corresponding enthalpy changes. The question says, what is the enthalpy change of dissociation? Dissociation means splitting. We are splitting of ethanoic acid into ethanoate and H positive. So we have tried this equation. CH3COOH. It will split up into CH3COO minus plus H positive. Now, how can I calculate the enthalpy change for this reaction? By applying Hess's law. Just keep in mind the delta HR in this reaction cannot be calculated directly, but we can calculate it using different other reactions. So we can manipulate these two equations in order to end up with this equation in here and then calculate the values. We can notice that the H positive is in the product side, but the H positive is in the reactant, and that's why we need to flip this beautiful equation. And if we flip these equations, we have to flip the sign of delta H, and it becomes positive 57.2 kilojoule per mole. So if we flip this equation, let's write it here. If we flip this equation, what happened? It becomes H2O. It gives you H positive and OH negative. Now we have CH3OH. It's in the reactant side, and this one here, it's in the reactant side. So there is no need to flip this equation. We keep it as it is. So it becomes CH3COOH plus OH minus CH3COO minus plus H2O. If we add the two equations together with their values, plus 57.2, we can cancel out the water. We don't need it. And we also cancel the OH for sure. So the remaining compound or the remaining equation is CH3COOH. It gives you H plus CH3COO minus. If you add the two values together, you'll end up with 1.2 positive, and the answer is B.